Okay, hello everyone, and thank you for being here. Welcome to our AutoML seminar today. I'm happy to introduce to you our speaker today, Jörg Franke, who is a PhD candidate in the group of Franke, and his research focuses mainly on online HPO, and currently he's also working on probabilistic sequence modeling for RNA folding. And today Jörg is going to present his ICLR paper, Simple Efficient Automated Deep Reinforcement Learning. So thank you, Jörg, again for being here, and the stage is yours.
Thanks for the introduction and having me here. I present today this paper, Sample Efficient Automated Deep Reinforcement Learning. So the talk will maybe a bit shorter than the other talks here in this format because it's just one paper. And this is a joint work with Gregor Köhler, André Biedenkam, and Franke. So, in the beginning of this work, we had the assumption that we want to use reinforcement learning in some real-world application. So we don't know anything about the task, we don't know the optimal hyperparameters, and we assume that the environment interactions are expensive or somehow limited. So we want to use as little environment steps as possible while finding the optimal hyperparameters for our algorithm and train our agent to the task. And our approach for this is our work here, Sample Efficient Automated Deep Reinforcement Learning, or in short, SEARL. And the key idea is to use an evolutionary routine in combination with the RL training. We use the neuroevolution, so we are able to adapt the architecture as well. And if you're familiar with PPT, you can think of PPT with the shared replay memory and for neural architecture as well. So to go a bit deeper into the approach, first in a nutshell, we have here on the right the graphic of the evolutionary loop. Like all evolutionary algorithms, we first initialize a population, we evaluate our population, then we select them, mutate them, and here in our approach, retrain them. This evolutionary outer routine allows us to find optimal hyperparameters while training the agents, and we're able to dynamically adapt the hyperparameters instead of find just one single fixed hyperparameter. And the shared replay memory allows us to save a lot of environment interactions. So now step by step. We initialize a population of n RL agents. In our experience letter, we used small numbers, 10 or 20 agents. All of them with different initial rates, and they could also have different hyperparameter settings. In our case, the hyperparameters are the learning rate, the architecture, but it could also be more like rate decay or reinforcement learning, specific parameters like exploration noise, stuff like this. By the way, if you have any questions, please ask right away. In the next step, or the first step, we evaluate the agents in the environment. So we run each agent for at least one episode or for at least a minimum number of steps. So we make sure that we get enough training data in form of environment interactions per evaluation. The performance of the agent in this episode is the fitness of this agent and serves later in the selection. We can perform this evaluation in parallel, so we can save here a lot of time. Just need a bit more compute. This replay memory here saves from all agents the transitions during the evaluation on one single place. And later in training, it serves as the replay memory to sample batches for the training steps. After we evaluate our agents, we can now select them. Here we use tournament selection, which means we create a subgroup, a random subgroup of X agents. Normally X is here a small number like 3, 4, or 5. And then we take the best of this subgroup and copy them to the next generation. We do this as often as need to have the same generation size as before. And we use elatism, which means we copy the best agent in any case. Alternatives here are roulette wheel selection or top K selection, but tournament selection is a bit more greedy than roulette wheel and less greedy than top K. So something in the middle here, that's the reason for this design decision. After we've created a new population, we're able to mutate them. So we apply one mutation operator to each RL agent. We choose them randomly. We can mutate the rates of the neural networks by adding noise. Here we can choose between the different amounts of noise we want to add. Or we can change the activation function of the neural networks. We can change the network size either by adding a layer or by adding a specific number of nodes. And the number of nodes we want to add is also randomly chosen. Or we can change the hyperparameters. So we can add some small value to the hyperparameter or remove some small value from the hyperparameter. And how much we want to add hyperparameter is also chosen randomly. Or we can do nothing, just keep the agent like it is. Later we will see that each of these mutations is somewhere beneficial. And next, and finally, we train our RL agents in the environment, in the use of the transitions from the replay memory. We train them for as many steps as we collected in the evaluation, or less. In our experiments, it was beneficial to have only 60 or 70% of the training steps regarding to the total number of evaluation steps in the evaluation phase. And this training can be performed in parallel, so it's somehow efficient. One thing special comparing to normal reinforcement learning training, we need to recreate the target network and re-initialize the optimizer. Because we changed the hyperparameters, changed the architecture, we have a different sized agent network, and to also adapt the target network, we recreate them in the start of each training phase. Also, the optimizer rates change, so we have to re-initialize the optimizer. So in total, this allows us to collect a diverse set of environment interactions in this replay memory, and the whole population benefits a lot from this diversity and results in a fast training progress. Now we see some experiments. We did experiments on use of the TD3 of policy algorithm on the Jörg benchmark suite and the QN on Atari games. We use as baseline random search, where we randomly search for the best hyperparameters, which we keep them fixed during training, and population-based training, and we modified population-based training, so we allow architecture changes as well. For a fair evaluation of hyperparameter optimization in reinforcement learning, we count the total environment interactions for training and HPO together. In the first experiment on TD3, we used 5 Mutation environments, and in each environment we had a population of 20 agents, initialized by a small MLP with one layer, 100 28 nodes. And we allow mutations to the architecture by adding one layer, adding 8, 16, or 32 nodes, changing the activation function, and we run each SEARL hyperparameter optimization for 2 million steps in the environment. The random search was performed on 20 randomly chosen configurations, and each configuration was trained for 1 million steps. And in PBT, we use a population size of 20 and trained for 100 generations. We see the results in the next plot, and each line is the mean of 10 random seeds. So here we see the blue line is SEARL, the red random search, and the green PBT. For SEARL and PBT, it's quite easy to count the total environment steps because they use during the optimization the environment. In random search, we have first the search for the best hyperparameters and then the best hyperparameter trained in the environment. So we use the final performance of this last best hyperparameter setup and squeeze them to fit it in one joint plot here. We see that SEARL is slightly better than random search, but takes 10 times less environment interactions. We can see the same effect for the other environments, so we get always the same or similar performance except the fit reacher, but require less environment interactions. Or differently, we can train with SEARL an agent while optimizing its hyperparameters. In the same time, we normally train an T3 agent with a fixed hyperparameter setup. Next, we analyze a bit more the different parts of this approach. Here we see the hyperparameter change of SEARL over time. Again, for all the 5 environments, in the upper plot, we have always the total number of hidden nodes, and in the lower plot, the learning rate of the actor and the critic. Different environments require different large NLPs, and so we see, for example, in Hafzeta or Reacher, the MLP over time is always increasing, while in AND it stops at a size of 500. Also, the learning rate of the critic is mostly decreasing, but the learning rate of the actor is sometimes also increasing. The values are always the values from the best agent in the population, and the plots contain 10 runs of each environment. We also did some ablation, and here we looked at the different mutations and the impact of the shared experience replay. We have SEARL in blue, and we have a version without shared experience replay in green, no learning rate adoption in the mutation in green, the no shared replay memory was yellow, no architecture adoption in red, and purple is no network rate mutations, so no adding of noise. The shared replay memory has the biggest impact to the training. Some of the other mutations are sometimes harmful, sometimes beneficial, but none of them is in all environments super harmful. So we kept all of them. And finally, we have the impact of the target recreation and optimizer re-initialization. The default here is in green, and we see that the optimizer re-initialization or the target recreation in blue and purple is sometimes even beneficial. Often both is beneficial. So it serves here as a regularizer. And yeah, maybe I have to say these are normal TD3 trainings without any hyperparameter optimization with a fixed hyperparameter setup. And the recreation and re-initialization is performed every 10,000 steps. So we can have a look at this more in detail in another work maybe. And here are the final architectures found by SEARL, and we see that different environments require different large architectures. So we have here difference between half-setter and hopper of double the size. And our algorithm is able to find the best fitting model size. We also did some experiments on DQN.
Jörg?
So, yes.
There's a question in the chat. I don't know if you want to take it now.
Yeah. I don't see the chat so far. Thanks. No, they are not done with spatial optimization. There are newer work which uses Bayesian optimization for some kind of mutation, but in our work we didn't use any Bayesian optimization.
How many GPU hours does the mutation or does the hyperparameter search take?
Yeah, let me think of this. We run all TD3 experiments on a CPU cluster, and one single run takes on the CPU roughly a day. And with SEARL we took 5 or 6 days for one run, and for BPT in a similar time scale. So it's not more expensive than BPT.
And why did it take 5 or 6 days rather than also 1 day? You previously said you can get it for the same performance, same cost as running a single run.
Yeah, because we didn't parallelize it optimally on the NeMo cluster. So it's some engineering efforts have to be made that it's more parallelizable.
But fundamentally, there shouldn't be a need for any slowdown, right?
Yes. If you spend more engineering effort, I guess you get the same time. Any more questions? Yeah, you're welcome. So experiments on DQN. We used rainbow DQN, but without prioritized replay memory, because we have our own replay memory. And we used 5 environments and trained a population of 10 RL agents. The MLP is initialized by the same size, and the CNNs are initialized with 2 layers and 32 channels. We allowed the same mutations on the MLPs, and on the CNNs we also allowed mutations on the channel size, the kernel size, and the sprite. And again, we run SEARL for 2 million arrival interactions. We only compared it to SEARL, to random search, because it's way more expensive, and use the best configuration out of 10, each trained for 2 million frames. In the next block, we see 5 random seed per experiment. Here.
Yeah, before you continue, there's another question. I will just read it out loud. And also, are there sort of layer depth regularizations that prevent the model to get too large?
Not yet, no, not at all. We could include this, but it wasn't necessary. So they stopped at some point and didn't get any larger.
Well, you started with really small networks and let them grow over time. So potentially, if you had run this for much longer, do you think it would grow, or?
Maybe a bit, but As we see here, they saturate at some point, so the numbers of hidden nodes stopped increasing. That's the orange here, the orange lines.
And actually, I think I might take back what I said earlier. Fundamentally, is there really no reason for any slowdown? So there is no overhead in the number of environment interactions. And that's kind of what the experiments show. But in terms of runtime, I guess, yeah, some overhead of the agent.
Yeah, but this is another design decision we have to make, and in the end, we want to avoid to get it more complex. And since it wasn't necessary, so yes, that's a good point. The runs of SEARL for DQN in the Atari environments. Again, we see similar performance as random search, so we find optimal hyperparameter setups, but with way fewer, 10 times fewer environment interactions. So finally, some limitations of our approach. It benefits a lot from the shared and diverse experience replay. So this approach will not work for on-policy reinforcement learning or supervised learning. It works in parallel, but it still requires more compute. So for small models, it's okay. For larger neural networks, which have to run on a GPU, could be engineering effort and requires more resources. There are many design decisions in the meter optimizations. So we have to make decisions on how do we select, how do we mutate, what are the frequencies of the inner and outer circles, and so on. Some of the decisions were backed by preliminary experiments, some of them by small grid searches, but some of them are just decisions handmade, like the decision on that we use tournament selection. That's always an issue in AutoML or AutoRL systems. Then it's quite heavy and complicated to use because it's not a handy framework, and since I'm the only developer, it has no really maintenance. And the last limitation is reinforcement learning. In general, it's heavy seed and implementation dependent. And it's hard to evaluate reinforcement learning algorithms reliably. So to conclude, we see that SEARL jointly trains an RL of policy agent and optimizes its hyperparameters dynamically over time, including the neural architecture. The most beneficial part is the shared replay memory, and we see that the SEARL population benefits a lot from this diverse set of experience in the shared replay memory. To this point, when you copy only this shared replay memory, you take the full replay memory and train a single agent on it. It trains way faster than comparing to collecting its own experience. So that's a huge plus here, this diversity. And finally, SEARL requires 10 times fewer environment interactions compared to population-based training or random search, and nearly the same time as a normal DDL T3 training. Thank you for your attention. For more information, please check out our paper or code. It's open sourced. Are there any more questions?